All right, ladies and gentlemen, this class recording has begun. So you'll notice two things about when I do class recording. One, usually stand up here a little bit more than I won't walk around quite as much because this is the microphone right here, so I want to stay close to that. And two, I'll generally talk louder because I'm trying to make sure the microphone picks me up. So if it seems like I'm yelling, I am. So, all right, section 4.4. So up to this point, we've discussed the big idea that started off this section being that horizontal and vertical motions are independent of one another. And as a result, over the first part of section 4.4, we have come across these equations, right? Oop, turn the pen up, there we go. There we go. We have come across these equations right here that relate the position of an object and the time to, along with the acceleration and stuff like that, but two equations, right? One for the horizontal motion, one for the vertical motion, because we have to analyze them separately. And then yesterday, actually Tuesday, we talked about the idea that independence of motion also applies to velocity, that we have a separate horizontal and a separate vertical velocity, and we can analyze each one of them separately because of the independence of the motion. The fact that they are occurring simultaneously doesn't change either one. They're completely separate of one another. Okay? That being said, if we fast forward here to conceptual example 4.11, which is at the bottom of page 4 of your packet, it says, two youngsters, whatever that means, dive off of an overhang into a lake. Dangerous. There could be rocks and stuff underneath. This is a public service announcement. I'm not encouraging any of you to do this at home, so, even in the name of physics. All right. So, although if you went to the hospital and they said, "What happened?" I said, "Well, I was trying to prove physics."
You can go to the rec center for that. They have a nice diet too.
See, you can prove physics and be safe at the same time, Niraj. That's the way I like how you're thinking, Niraj. Niraj, I have a feeling that once word gets around that your comments are on these class recordings, the viewership is going to go up. I mean, my number of views is going to go way up. So, what? Generally less than 10, and some of them are me just checking to make sure it actually posted properly. So, it depends. It depends on what we're doing. The physics recordings, not so much. The physical science ones are a little bit more because they're freshmen and they haven't given up on life yet and stuff like that. So, but. Let's be serious, right? Watching the class recording requires that you actually go home and do some homework, right? That's. So. I did read a nice article yesterday about how some guy wrote a book recently. He's a psychologist. Basically said that school in its present form, the way that we have school, first was not at all based on any kind of scientific research about how people learn. It was basically developed out of the Protestant Reformation. Basically to teach kids to sit down, shut up, and read the Bible. That's pretty much what school was intended for. And as a result, nowadays, kids don't learn very well as school is currently constituted. So, shocking, I know. That's big shock. But, so, anyway, I'm sure this video will get lots of commentary as well. So, I'm just saying. I didn't say anything derogatory about religion. I said school was intended to get kids to sit down, shut up, and read the Bible. That's what it was. That's how it developed. So, but anyway, all right. So it says two youngsters dive off of an overhang into a pool at the rec center. Just so make sure we're being safe. Diver 1 just drops straight down, but diver 2 takes a running start, runs off the cliff with an initial horizontal speed equal to v. Is the splashdown speed of diver 2 greater than, less than, or equal to the splashdown speed of diver 1? Okay, so diver 1 just sort of steps off the edge, falls straight down. Diver 2, though, takes a running leap and ends up over here. Okay, so it's asking about splashdown speeds. First, diver 1. Diver 1 is basically just a kinematic equation problem that we did back in chapter 3, right? One dimension, straight down, acceleration 9.81. If we were to draw, some arrows to represent the velocity of Diver 1, Diver 1 would start off with a small velocity. Oh, that's just a straight line, not an arrow. Oh, yeah. Okay, so Diver 1 would start off with a small velocity, and then that velocity would continue to get bigger and bigger and bigger as he fell towards the lake, right? That's what happens to the velocity of an object that is accelerating, okay? But Diver 2, we have to worry about two things, right? Diver 2 is affected by gravity, and therefore all of these arrows would apply to Diver 2 as well. But Diver 2 is also doing what? Moving horizontally. So if we're going to talk about, Diver 2's speed, we have to take into account both his horizontal motion and his vertical motion. So, at this point, oh, that is not what I wanted. Sorry. Yeah, there we go. All right. So Diver 2 is going to have that same vertical velocity that Diver 1 has, but still maintaining that horizontal velocity as well. What did we say about the horizontal velocity of a projectile? Look at the previous page of your packet. Find the equations that talk about the velocity of a projectile, right? What do we see about the horizontal velocity of a projectile? Final, same as initial. So we would describe that velocity as constant. Horizontal velocity is constant. Why? Go ahead, Dylan. There's nothing acting on it. The only thing affecting the motion of this object is gravity, and gravity acts vertically. So the horizontal velocity remains the same the entire time, right? So that's going to be your x, right? Yeah, horizontal x, yep. Okay, that's horizontal is the x-axis of an xy axis,
so
right?
Any problem with like the x and y chart?
Yep.
The x vi and x df are equal.
And sorry for people watching the recording, that was a thumbs up with a stamp, right? Because that was important for emphasis. Right? Christina, that's going to be important later on today, so we're gonna talk about that a little bit more as we go along today. So, but yes, that's an important idea that for any problem where we're dealing with projectile motion, if we can assume that gravity is the only thing acting on that object, horizontally there's nothing to change the velocity, therefore it will remain constant the whole time. Okay? But that's not true of the vertical velocity. The vertical velocity continues to grow. So this object 2, continues to speed up, but what its actual speed is depends not only on the vertical velocity that is increasing, but also the horizontal velocity. So if we have two vector quantities, to find how they combine together, right, we have to find the resultants. Meaning, we have to find the resultant of the horizontal and the vertical velocity in each of these cases. So let's say this blue line represents how fast Diver 1 was going when he hits the water. That same blue line would represent how fast Diver 2 is going vertically, right? But Diver 2 is also going horizontally. Christina, go ahead.
So you made the blue and the under where it says like 2, Diver 2.
Yep.
Is that green arrow? Is that the triangle we're looking at? Is that a
Yes.
component of the triangle we're looking at?
In this case, the final speed of diver 2 is the resultant of his horizontal and his vertical.
So that line you mean?
This one?
Yeah.
Yes, that's what we're actually looking for. I didn't draw my arrows exactly the same length as the one in the picture.
So finding the resultant
Yep.
of that.
Yep.
Oh,
Because right now, Christina, are those vectors lined up properly for us to find the resultant?
no.
They have to be lined up how?
They have to go
Ooh. Right? Because they have to be lined up head to tail, right? And then, even though it's not along this line that is drawn on your picture, right? According to my two vectors that I drew, that purple would be the resultant. And because one's horizontal and one's vertical, what has to be true about the angle between them? If red's horizontal and blue's vertical, 90 degrees, and that makes purple the hypotenuse of a right triangle, right? Raj, go ahead.
So what about the one in the upper corner? Like, isn't it?
This one?
Yeah.
This arrow right here, again, even though my arrows that I drew aren't exactly representing it, the length, because I drew mine a little bit longer, that would be his speed at that point in time.
Yeah.
It's still the resultant of the horizontal and vertical.
Okay, so one with the blue arrows, what are the others?
This one?
Yeah.
Yeah, we would have, if we wanted to find out what that actually was, right, we'd move blue over like this, right, and then we'd find the resultant of those two. Because this blue, well, I'll ask you, Niraj, how does this blue compare to this blue? Which one's faster?
Well, they're both going the same speed.
What's happening to those blue arrows as he continues his flight? They're increasing because those blue arrows represent what, Tyler? It represents the vertical velocity, right? What's happening to the vertical velocity? Because of gravity. Does that make sense, Raj?
Yep.
So these blue arrows keep getting bigger and bigger. What's that going to do to the hypotenuse? Oh, sorry. What's happening to the red arrows? So red arrows are staying the same because horizontally we don't increase. So, Raj, if one side of the triangle keeps getting bigger, what's going to happen to the hypotenuse? It's going to get bigger as well. The hypotenuse representing what his actual speed is at that time, right? Because it's a combination, the resultant of those two vectors. Okay? All right, it's good there? Okay. Let's take a look next at page 5 of your packet. And on page 5 of your packet, you should see... Oh, sorry. You tell me.
equal.
Nope. Which one's faster? Diver 1 or Diver 2? Diver 2. Because Diver 2's speed is the resultant of the horizontal and the vertical.
So it's bigger than that blue side.
Right? Does that make sense? Okay. Because we have to find the resultant of those two. Sorry.
Because the diver 1's blue arrow is the same
Yep.
as diver 2's.
Good. These two blue arrows are exactly the same because vertically they're doing the same thing, but in Diver 1 we have to include that horizontal part, and that's why Diver 2, I think it's, as I said, in Diver 2 we have to also include the horizontal motion as well, so Diver 2 is going to have a greater splashdown speed because it's the resultant of the two. And like you said, Christina, those two blue arrows are exactly the same. Okay? All right, good there? Okay, let's take a look at page 5. And on page 5, let's look at guided example 4.12. Okay? I know I'm skipping over a little bit, but there's a reason why. Okay? All right, so it says, chipping from the rough. A golfer sends a ball over a 3-meter high tree that is 14 meters away. The ball lands on the green, of course, at the same level which was struck. So it says, the ball lands at the same level at which it was struck after traveling a horizontal distance of 17.8 meters. So part A says, if the ball left the club at an angle of 54 degrees above the horizontal, landed on the green 2.24 seconds later, what was the initial speed? Part B, the ball passes directly over the tree at 1.76 seconds, how high was the ball at that time? Okay, a lot going on, right? But let's go back to how we address these issues, all right? Because this is a projectile motion problem, right? We will address it and set it up exactly the same way that we set up the projectile motion problems before. So, start with your chart. Alright, and then the 6 things down the middle, right? Where did it start on both the x-axis and the y-axis? Where did it end on the x-axis and the y-axis? Positions, right? What was the initial velocity? What was the final velocity? Acceleration and time. Alright, so start with the same chart that we've done up until this point. Okay? Now, though, let's start making some adjustments. Okay? First, what is this question asking us to solve for? Let's go part A. Sorry, let's go part A. Initial speed, right? However, what was its initial speed? If we take a look at the picture, especially here at the beginning, this problem starts a little bit differently, actually kind of a lot differently, than the problems we've done up until this point, right? The problems that we've done up until this point looked more like this, where when it became a projectile, which way was the object going? Horizontally, right? So the initial velocity on the vertical side was 0, right? That's all familiar? Yes, no, right? But here, looking at this picture, this object, the golf ball in this case, does not start with an initial vertical velocity of 0. It's launched into the air. When it first becomes a projectile, it's actually doing 2 things. It's traveling both horizontally and vertically at the moment that gravity starts acting on it, because that's how it gets hit or launched. Okay? So, similar to what we just did in the previous problem, if we want to know the initial speed, ultimately we're going to have to find what? In the last problem, when it asked us to find speed of the splashdown of Diver 2, what did we have to find? In the last problem, when it said what was the splashdown speed of Diver 2, the hypotenuse, or the resultant, right? Guess what we're going to have to find here to find the initial speed? The resultant, okay? The resultant is a combination of 2 vectors, right? The vector sum. So which 2 things are we going to need to find first before we find the resultant? Kai, what are you going to say? That will help us a little bit later on, but where is this question asking, what is this question asking us about? At the beginning, right? And it's asking us about what at the beginning? The speed. Therefore, we're going to have to know how fast was it going horizontally and how fast was it going vertically, right? 2 unknowns in this problem, because the actual speed is the resultant. So we have to find both of those so we can find the hypotenuse of that triangle. Okay, good so far. All right, we said, now, let's start attacking this, all right? First, we said there are two things that we can fill in right away, right? Even before reading the problem, we said there were two things. We can fill in the accelerations. This is still a projectile motion problem. Even though it starts differently, it's still an object moving in 2 dimensions. And when that's the case, the only thing acting on it is gravity, right? And therefore, the vertical acceleration is going to be 9.81, and the horizontal acceleration is going to be 0. Okay.
Whatever the minus sign in front of 9.81.
So, the minus sign is a direction, right, Naranj?
Yes.
And in this problem, they've chosen the spot where the golf ball was initially hit as the origin,
Yes.
right? Meaning that if this is the y-axis, up positive, down negative, right? So we can make that negative 9.81, right? All right, now, let's start attacking things in this problem, okay? Naranj, we just talked about. They've chosen the spot where the golf ball was initially hit from as the origin. That gives us 2 more things on this table. 0, 0 for the initial positions, right? So the initial position y is 0, and the initial position x is 0. Okay? It also gives us information in the problem that tells us the final position on both axes. Collier, go ahead. Okay, so it says it travels a horizontal distance of 17.8. That makes x final 17.8. Okay? Say again. Y is going to be 0 because the ball lands at the same level at which it was struck. Is that good? Meaning on the y-axis, it starts here, it goes up, but then it comes back down. So the final position is the same as the initial position on the y-axis, right? It doesn't end and begin in the same spot because we have to take into account both of those dimensions. But on the y-axis, it goes up and it comes back down. So y initial is 0, y final is 0. Collier, go ahead. Okay, hold on one second. Let's get Christina's question because that's the next thing we're going to fill in. Christina, go ahead. Did you have a question, Christina, or do you want to give me some more information?
No, I got a question.
Okay.
I figured it out.
Okay.
I didn't know if you did the second. If it did get the second,
This problem becomes harder, but not impossible.
do we use the y equation sine t and then put it back into the x?
Let's do this. So Collier, what were you going to say? Okay, so it says, right, lands on the green 2.24 seconds later. What did we say has to be true about time in both columns? Has to be the same, right? Because both of those motions are occurring simultaneously, right? Christina, to build on that, right? If we didn't know the time, if they didn't give it to us in the problem, right, we could solve it any way that we can solve for time using any one of the equations that we have used so far, okay, would give us the time for horizontal and vertical. So yeah, keep that in mind, that if we can find time in any one of those equations that we've used up until this point, that will give us the time in any of the other equations, because it always has to be the same. All right, good so far, okay? Now, this is a pretty big paragraph, right? Lots of things, and we have filled in almost our entire chart based off of that, what we've figured out so far, right? Good there? So, the 4 equations that we have used so far still apply to this motion. So remember, we had 2 equations that relate position in time, and we have 2 equations that relate velocity and time, right? Any one of them still applies to this motion, okay? So as long as we can find v initial in any one of these equations, we're good to go to find what we need to find. Even though this object started off differently than the objects in the previous problems did, right, we're still good to go to use them.
So we can't use the second set because
We
we don't know what the final velocity
don't know the final velocities, so that eliminates the second set of equations because we don't know those, okay? Although, hopefully not to confuse you, right? But we do know that horizontally, those have to be true, but if we don't know one, we don't know the other one, right? So that's going to take us back to the first set of equations, right? X final equals x initial plus vixt, and y final equals y initial plus vixt plus 1/2 gt squared. Okay. Good there?
Wow.
Thank you. I was testing those. All right. So you should be able to use both of those equations to find what we need to find. Okay? I will do them up here because one of them gets a little bit tricky. I do. I had to put the third term down a line because I ran out of space. So, yeah, this is all one thing. So. Good with those two? First, good. First, keep in mind, right? This is negative 9.81, but to solve this problem, we'd have to take it over to the other side, so we end up adding. Say again? Right, this whole term would be negative, right, but to solve this equation for this variable, right, we have to take that over to the other side. So this does come out positive, even though we have a negative acceleration. That's okay, all right? No, that's just more of a coincidence. No, I mean, that's more of a, for the next part, Christina, just, okay? Just make sure that we understand, right, that, X is always gonna be in the same direction, because if there's no acceleration, it's always gonna be in the positive direction. But Y can be up or down depending on the problem that we're doing, okay? All right, but what did this problem ask us for? The initial speed, right? This is the initial speed on the x-axis. This is the initial speed on the y-axis. But to find the initial speed, we need to do what? Find the hypotenuse or find the resultant, right? Okay. There's an initial speed on the x and the initial speed on the y. But going back to this picture, right? When the guy hits the golf ball, it only goes one way, right? There's one path that the golf ball takes.
But would that not be the hypotenuse? Would that be a line in the middle?
Which is the hypotenuse.
The lines here, the lines here.
Yep.
The hypotenuse is this. But the lines going through.
Remember that we can move our vectors anywhere we want, right? So, if that represents the initial vertical velocity, right? And this represents the initial horizontal velocity, right? They're not lined up properly for us to do this, right?
I was thinking it was like the entire x and y axis.
This one, right? That ultimately, that's the one that we have to find, right? Okay? But now we know the two sides of that triangle, so we can figure out what that's going to be, right? So go ahead and do that real quick. It's the velocity, right? Good.
So is that, including all of the results?
This is Pierce, that's the initial speed of the golf ball. This is how fast it was traveling when it left the face of the club, okay? These two would actually be the components of that initial speed. Does that make sense?
Yeah.
Going back to the fact that in the first section, any vector that we have that isn't completely horizontal or completely vertical is a combination of two vectors, right? So yeah, so these two that we figured out actually are the components of the initial speed. This is the initial speed itself, okay? Good there. Okay? All right. We are not going to have time to do another example problem. So,
Are we going about to predict our angles tomorrow?
then we'll do that tomorrow in round, yeah. So we'll do an example problem like that where we have to use those angles tomorrow, and then I'll give you some time to do some practice in class tomorrow. Okay? By the way, good job today, everybody, with the class recording. It was, entertaining and informative, I have to say. So well done.
At the end of the day, and did that lab.
Yeah. So just to keep you on your toes, right? There is a little bit of homework for tonight. Some of them are conceptual questions, but some of them are also some calculation problems. So we'll talk about at least one of these tomorrow at the beginning of class and get into the angle stuff, okay?